longitudinal wave, this and this are not particularly convenient. So I can express this as a graph. If I think I've got some sort of ambient distance between particles or air pressure or distance between coils. And so if it's rarefied, it's below that, and then it peaks there, and then it's rarefied again, then it peaks, and then it's rarefied again. So I can express a longitudinal wave in a classic, if it's a constant frequency, I can express it, like a sine wave or a cosine wave. Transverse waves, I can also represent them the same way, just in a transverse wave, this could actually be just the side view of what you're actually looking at. So physically, I have something that is moved in this direction or moved in that direction. Questions here before I show off the extent of my knowledge of geology, which will connect to this? Earthquakes? Yes. Two more examples. A longitudinal wave, in geology there's these things called P waves. In transverse waves there's this thing called an S wave. Any of you had geology or in a family with geology? Okay. So correct me if I'm wrong.
It's been a while, like the first class I took here.
Ah, okay. My knowledge of geology comes from my wife. So P waves, the P stands for one of two things. It stands for pressure or primary. S wave stands for shear or secondary. So if I have an earthquake here, and I have a seismograph over here, and I'm going to do a seismograph based upon my limited knowledge of them. They're more sophisticated than this, but my wife did some graduate work looking in the Bat Creek area of North Carolina when they were building the power dump, whatever they call it. They were doing construction a couple decades ago. And the point was to, during low electricity use times, Bat Creek Reservoir, that's what they're doing. You have water down here, and then you have a reservoir here. So during low use times, they would pump water into the reservoir. And then, when suddenly you needed more electricity, they would then drain this back into the lake down here, taking this potential energy, converting that into kinetic energy I'll just label it as a paddle wheel. They'll take this potential energy, convert it into kinetic energy, which then gets converted into electricity during high peak times, peak usage times. So we were up there during the construction, so they were doing a lot of blasting, and so what my wife would do is together, we would set these things up, and this is a drum that basically had a piece of paper on it, and then we would smudge it. We had this thing that gave off black smoke. We covered the whole thing in essence, black soot. You put it up to a battery so that it would rotate, and you have a needle that basically drags through it. And when an earthquake or there's an explosion, the needle will move, and so you'll have etched into the soot description of the motion. Anyway, there's an earthquake here, and so shock waves are being sent everywhere. Primary waves are the first waves to actually get here, thus primary. They are caused by pressure. The fact that I move this piece of earth, which pushes on this piece, which pushes on that, which pushes on that, and so on and so on. The secondary waves are the shear waves. If you ever hear the term shear in reference to geology or physics, shear typically deals with forces that cause I guess, transverse displacement. So if I applied a shear force to this, I'm applying it that way, which perpendicular to the main line. So you also have these secondary waves, which get there second, or shear waves because it's causing the earth to move one way, causing the next bit to come up with it, and so on. Which then brings up the question of, why do primary waves get there first? Is it just that pressure waves travel faster than shear waves? Well, maybe, but the bigger thing is pressure waves can travel through liquids, solids, gases. Sound obviously travels through a gas right now. So these waves definitely go through it. Shear waves, though, do not travel well through liquids and gases. So if they did, then if I did that, you would feel the breeze back there. And I'm guessing, unless you're incredibly sensitive, none of you felt that breeze. Because as I'm dragging air molecules with my hands, it's not really attached to the next one. And you need a solid or something like that so that when it gets pulled, it pulls the next thing with it. So shear waves, or these secondary waves, must travel through solids.
So what's that in the difference between like a paper fan? Like if I did this, I can't really feel it, but the second I do this, I can.
It basically air's flowing between the fingers. I mean, you can do that and feel that, but
I
paper
don't
fan,
like
you got.
looking at it too much.
Oh, you don't feel that?
Well, I mean, like even if I do like this, it's like the same distance. I can't feel that from here, but then I can definitely feel this.
It's
for the same distance.
It's pushing more air. I mean, with the hand this far away, it doesn't. Yeah, I would think you feel a little bit, and if you're really sweaty, you would feel that. But because, well, think about sound. If with sound, my vocal cords have to vibrate back and forth fast enough to really smack one molecule into the other molecule.
Mm-hmm.
Whereas you're doing this, you're not flapping your hand fast enough. What is the sound of one hand clapping? Well, if it's going fast, but even like that, if I can move my hand fast enough, you would hear the clap.
Mm-hmm.
But it's just like, I probably would do major injury to my hand if I could go it that fast.
Mm-hmm.
So because the pressure waves can travel through liquids, solids, gases, and plasma, we figured out that the core of the Earth has to be, it's not solid. Whereas, since the crust is solid, secondary waves are going around like that. Pressure waves are going through. They will get there first. Even if they're not as fast, they're not traveling as far. And that pretty much is the extent of my knowledge of geology. Anything I said that
I don't remember anything wrong about what you said.
Okay. Questions to hear before we pull out the long coil? Then it's time for the long coil. I need a volunteer.
Sure.
Thank you, Dominic. Now, we were dealing with the harmonics with a fixed end, actually two fixed ends, and so we need to sort of address the fixed free end bit. So two fixed ends. The first harmonic, the simplest way that you can make is that. This is typically the way it's drawn, where you have the points that are not moving, and the point that's moving the most. I'm not claiming that it's in two places at once, I'm just claiming that, well, if it's going fast enough, it looks like it's two places at once. But this is a node, this is a node, this is an antinode. And this is the first harmonic. how many waves is that?
1, 2, 0.
It's not 1, it's not 2, it's not 0.
3?
They're going in the wrong direction, and it's not negative. Right, a wave, that's a full wave right there. Or if we did it in terms of harmonics,
So it's half a wave.
yeah, this is a half a wave. So if that distance there is L, L would be equal to a half of a wave. And so this is the symbol for wavelength. So L is half the wavelength, or the wavelength is twice L. I know that speed is equal to frequency times wavelength. We talked about last week, before. And so speed isn't dependent upon frequency and wavelength. It just happens to be equal to frequency times wavelength. Speed actually is tension over, and we can't use mu too many times, linear density. This is tension. Some textbooks will use lambda for linear density, but that'll be awfully confusing because that's the symbol I'm using for wavelength. Linear density is mass per length. So I have a certain tension in the coils. I have a certain linear density of the coils. Now there's a certain amount of mass per length. So once I have the tension set and the number of, and the coil density, how fast that wave is going to travel is set. So if I want a particular wavelength, I have to adjust my frequency, which is what I was doing out there. So the frequency is going to be the speed divided by the wavelength, which in this first case, for the first harmonic, is V over 2L. This formula right here, we'll go into more detail later about that formula. Just sort of presented it for now just as we're going to pretend it's true.
What is the last one? Mu is equal to ML.
M over L.
There's nothing to the right of it.
That's an arrow.
Okay.
Regular density is mass over volume. Surface density is mass over surface area. Linear density is mass over length. Second harmonic. I got a fixed end is going to have a node at the ends. If the end is fixed, it's a node. If the end is free, it's an antinode. And I'm going to add a half a wave every time. The node in the middle should be halfway. I can't draw, so the second harmonic, I have node. I have 3 nodes and 2 antinodes. How many waves is that? 1. Yeah. So L, the distance from end node to end node, is equal to 1 wavelength, or with the fancy math, wavelength is equal to L. And so the frequency in order to produce this, given a certain speed, is V over L. So I have to double the frequency in order to get the second harmonic. Third harmonic. I have a node on each end. that.
1.5.
So L is equal to 3/2 of a wavelength, or the wavelength is equal to 2/3 of L. You can also look at it this way. I tend to think of it in terms of how many wavelengths do I start with and then solve for wavelength, but also that's one wavelength right there. I got 2 of these loops, that's a wavelength, and that's 2 of them out of 3, that's 2/3. The wavelength is 2/3 of the total length. And so the frequency, assuming I have a set speed, would be V over 2/3 L, or 3V over 2L, or 1.5 V over L. So to go from the first to the second harmonic, I double the frequency. To go to the next harmonic, I increase by 50%, and then how much I have to increase the frequency to get to the next harmonic gets less and less as I go. I will say that some textbooks will come out with these formulas that they'll come out with a different formula for the 2 fixed ends, or the 2 free ends, or the 1 fixed, 1 free, and it'll depend on either the number of nodes or anti-nodes, and I never keep that stuff straight. What I recommend that you do when faced with a problem like that is just start draw the first one, the second one, the third one, and when you see the pattern, now you can project out to the 50th one. Because each harmonic, I'm going to add a half a wave, and that's regardless of 2 fixed, 2 free, or 1 fixed, 1 free. I have the 2 here. I don't. Okay, so the other one. Now, we can create these harmonics, and this will happen today, but over here, we have the string vibrator. The string vibrator basically is going to oscillate up and down 60 times a second, assuming that we just plug it into the outlet, or we have a device over there, and so we can adjust the frequency. But from that, we can actually we can make predictions over, if I know the tension in the string, and I know the linear density of the string, I can start predicting how much tension I can start making predictions. Typically, I can see the harmonic. If I see the harmonic, then I'm going to rush through this, and I prefer not to. So that will just be sort of a teaser for Wednesday when you got the homework quiz on chapter 8. But we'll have enough time to play around with the string vibrator.